This lesson starts off by revisiting the concept of continuity. To be exact, we're going to talk about whether a function is or is not continuous at, keyword, at a particular x value. We have previously discussed the definition for a function being continuous at a particular value, x equals a. And here it is. If you recall, the limit as x approaches a of f of x has to equal the value of the function at x equals a. And we explored this visually, and we talked about the definition sort of conceptually, but now we're going to do a proof that utilizes this definition. I like to break the proof down into 3 parts. I find that if you break it into 3 parts, you will not forget a important portion. Okay, step little I. I like to evaluate the function at the point in question. In this case, x equals -1 is the point in question. So I'm simply going to evaluate p at -1. To evaluate that, I look up here at the piecewise function, and when x is not equal to -1, it has the behavior on the top, but when x is equal to 1, it has this behavior. So we simply have to plug it in to the piecewise function in the part that applies. So that's just going to be secant of -pi minus the natural log of -1 squared, which is 1. I'm going to evaluate this. Okay, so we have the secant of -pi. If I think of what is the cosine of -pi, I know that is -1, and 1 over -1 is also -1, minus the natural log of 1, which is 0. So I have evaluated this to be -1. Typically speaking, this is a little weird. Typically speaking, they meaning the author of the question, would simply replace inside this green box with a -1. But this is a way for me to get us back into thinking of some of these trig and transcendental evaluations. At any rate, we computed in step little I that the function at -1 is also -1. Step 2. In step 2, we want to find the limit as x approaches -1 of the function p of x. So I would like you to write the generic function p of x or f of x or whatever function's given, and then that's going to be followed by the behavior of the function as we approach -1. As we approach -1, we have this top behavior. When we equal -1, of course we have the green, but when we approach -1, the behavior of p is x squared minus 1 over x plus 1. And if you remember from pre-calculus, to evaluate this limit, we may have to do some manipulation, you might say, and then simplification. I can see here that the numerator factors to x minus 1 times x plus 1. The denominator is x plus 1, so that's really nice. We see these are going to cancel. So that's going to be the limit as x approaches -1 of what is simplified to x minus 1. Now, since I can substitute it in, I will. And that's going to be -1 minus -1. That comes out to be -2. Now, in the final step, step 3, I always want to see in this final step the definition present, the thing I have in pink. So here, I'm going to say, therefore, the limit as x approaches -1 of p of x, and I'm going to compare that to p of -1. And if you see here, the value of the function was -1, and the limit was -2. So these most certainly are not equal, right? Because this is equal to -2, and this is equal to -1. But the important part here is that I draw this definition and I write a not equals, because from that, I then conclude these 3 dots mean therefore, p, the function p, is not continuous at x equals -1. If I graph the function p of x, I see that we have a hole in it, and that a hole has been displaced by this point up here. And so we can visually see that this is not continuous. See, the limit is approaching -2, but the value is -1. They're not equal. The function is not continuous. Let's do a similar proof for f of x. And number 2 here, prove f is or is not continuous at x equals 1. So in step 1, I'm going to evaluate the function. So f of 1 equals, I have to decide, do I plug it into the top or the bottom? I see that we have an equals here, so I'll plug it into the top. 5 minus 2 times 1, and that is 3. Great. Step 2. I want to find the limit as x approaches that 1 of the function f of x. And that equals, and I'm going to say question mark. See, I'm pausing here because in this function f that I see above, the behavior to the right of 1, I've circled in green, is different than the behavior to the left of 1. And so in order for us to determine what the limit is, I have to consider each of these respective one-sided limits. Let me just change the color. Okay, so I put a little box here. This is just saying that I'm starting a new sentence. I don't have to put the box, but I like to. So I'm going to say, find the limit as x approaches 1 from the right-hand side of generically f of x. Please write the generic first. Then that's followed by the limit as x approaches 1 from the right of the behavior to the right. See, the behavior to the right is identified here, so I'm going to write in the green portion of the function. And when I plug that in, it also comes out to be 3. Excellent. Now, underneath, I'm going to find the limit as x approaches 1 from the left of f of x. And that's the general, followed by the specific behavior. Make sure you keep these negatives going to indicate from the left. And now this is the behavior to the left. Okay, when I plug this in, it comes out to be 2. Ah, behold. So what is the conclusion now? Please don't skip to saying it's not continuous. That is true. But locally, what we're concluding is simply that the limit as x approaches 1, period, does not exist. See, if the limit from one side does not equal the limit from the other side, then the limit itself does not exist. And since the limit does not exist, we go on to step 3. It is impossible, if the limit fails to exist, it's impossible to equal anything else. So here, the limit as x approaches 1 of f of x is compared to f of 1, so we'll say is not equal to f of 1. This does not exist, and this was equal to 3. And now that I have this statement, I'm going to conclude. My grand conclusion is that f is not continuous at x equals 1. And the graph of f of x shows us here our discontinuity. We have a jump discontinuity. I would like to briefly discuss a theorem that we will prove later, but I just want to get an intuitive sense for this. I say here, if D, then C, or in other words, D implies or guarantees C. Now, what do I mean by D and C? A function is differentiable at x equals a, that will indeed imply or guarantee that the function is continuous at x equals a. So if a function has a slope, then I know for a fact it must have also been continuous. The converse of this statement says, if C, then D. In other words, if a function is known to be continuous at x equals a, that would guarantee that the function is differentiable at x equals a. But we know that to be false. This one is not a true statement. See, I can draw a function that is continuous with a sharp transition, but it's not differentiable. So I cannot say the converse. In logic, we learn that converses are not always true. So if it is continuous, we cannot guarantee it has a slope or has differentiability at a point. the inverse of the original statement. I'll call this here the original statement, which we will prove, so it's true. The inverse of the statement says that if it is not differentiable, that would guarantee that it's not continuous. But for the same reason, here in this graph, that is not a true statement. The inverse of our original true statement is not a true statement. In logic, that is a known fact, that the inverse is not always true. See, it's not differentiable. See, this one here is not differentiable either. But not having differentiability does not tell us whether or not it is continuous at the point in question. We would have to investigate further. So if it's not differentiable, we'd have to investigate whether or not it was continuous. But there is a logical equivalent to the statement that I have above. And you may be saying it to yourself now. The logical equivalent would be what's called the contrapositive, which says if not C, then not D. And this is one I think we have an intuitive sense for. If a function is not continuous, well, yes, then we can guarantee there is not a derivative at x equals a. So picture any function that is not continuous at a point, x equals a. Here's an example. This one is not continuous at x equals a, and since it's not continuous, it guarantees there's not a slope or a derivative at that point. Another one could be a jump. Since it's not continuous, that guarantees it's not differentiable at a point. So we will prove this original statement above. We're going to prove that this is true eventually. And in proving that, we have also proved this. But know the connection. If we know it's differentiable, it has to be continuous. If we know it's not continuous, we know that it's not differentiable. This brings us to the major point of the lesson. In fact, the major point of the unit. If I have a graph of some function y equals f of x, I should be asking myself two questions. Number one, is the function continuous at x equals a? Now, we can do that visually by looking at whether or not we pick up our pencil to pass through the point at x equals a. So visually, that's a fairly easy task. Also an easy task is visually to determine if a function is differentiable at a particular point. And a sharp transition, we would say no, it's not differentiable. A vertical line tangent, we would say no, not differentiable. At any point it was not continuous, we would say no, it's not differentiable. So it's quite easy to do that visually. Now we will investigate what happens if we have an equation for y equals f of x. The question of whether or not a function is continuous at x equals a needs to be explored a little more formally using the definition, and we did that already in the warm-up of this lesson, which is seeing whether or not the limit as x approaches a of the function f of x equals f of a, and we did a proof of that. And to determine if a function is differentiable at x equals a, here we would also use a definition. But the definition that we want here is a definition that utilizes the limit of a difference quotient. So we would be asking, does the limit as h approaches 0, or delta x approaches 0, of f of a plus h minus f of a all over h exists? If the answer is that limit of the difference quotient does exist, then we answer yes, it has a derivative at x equals a, or is differentiable at x equals a. So let's take a look at three critical examples. Part A, prove that f is or is not continuous at x equals a. I would advise you to press pause and work out this proof on your own. When you're done, let's check with my work. And here's the work, and I'd like us to point out a couple items. F of 0, I need to decide if I plug it into the top or the bottom. Here I'm plugging it into the bottom because the equal sign tells me which behavior happens at x equals 0. Then I ask a question about the limit. I put a question mark. The only reason that I have two bullets here and writing two separate statements is because the behavior is different on either side. See, the pink is what happens to the right of 0, and green is what happens to the left of 0. If the behavior to the right and the left were exactly the same, well, I wouldn't need 2 bullet points. I would only need one statement. I would also like to point out that I'm using the generic first, followed by the behavior. See, I'm using the pink for this one. I'm also using the plus sign to indicate that's what happens as we approach from the right-hand side. Likewise, I'm using the generic here, followed by the specific. I'll ask that you do the same. I also highlight that I'm using from the left-hand side. I conclude that the limit is equal to 0 because these two are the same. And then I write the definition. This time I'm using an equal statement, concluding that f is in fact continuous at x equals a. Knowing that f is continuous at x equals a does not tell us whether or not the function is smooth or differentiable at x equals a. We have to investigate further. And that's a big part of this lesson, to find whether or not mathematically the function is or is not differentiable at x equals a. So if I'm trying to find whether or not the function has a derivative at x equals 0, then I'm really exploring this particular limit. I'm asking, does the limit as h approaches 0 of f of 0 plus h minus f of 0 all over h, does it exist? Notice again that the behavior to the right and to the left are different. That means I again will need two different limit statements. But be careful. I'm not just writing limit statements. I'm writing limit of the difference quotient. So I'm going to find what is the limit as h approaches 0 from the right, meaning delta x is getting smaller but inching up from the right-hand side of, generically, f of 0 plus h minus f of 0 all over h. Now your textbook doesn't mention this. I like to use this notation, f prime of 0 from the right. I think that organizes our work well. Anyhow, I am now going to plug in the appropriate behavior. I need to plug 0 plus h into the right side behavior because h is a positive quantity getting smaller, and positive is going to put us in the pink arena. So this is going to be 0 plus h squared minus 0 plus h. That's the pink. And then we found in part A, we actually found what f of 0 was. We found it was, in fact, 0. That's this portion here, all over h. Now this just becomes a repeat of some of the algebra that you've done a couple times. The limit as h approaches 0 from the right. Oh, this here is going to be h squared minus h over h. You can see, I'll go ahead and write this, although not every step is required here. If I factor out a h, we have this. Great, let's write definitely what it reduces to. It reduces to h minus 1. Now I can plug it in, and I get negative 1. So the slope from the right is equal to negative 1. Now let's investigate the slope from the left. This time it's the limit, and it's kind of a pain. We're writing what seems like the same exact information at first, except from the left, f of 0 plus h minus f of 0 all over h. And then it's the limit as h approaches 0 from the left. Now I need the behavior to the left, so I'm plugging into the green, 0 plus h minus, let's put a bracket to separate the one portion from the other portion. And this doesn't change. F of 0 won't change. F of 0 is always f of 0, which in this case is 0, all over h. And I'll try to speed this up. This is the limit as h approaches 0 from the left. I have negative h over h. Please know that I'm not plugging in here. I can't plug 0 into a denominator, but I can simplify first. And I can simplify this to negative 1. Now the limit of a constant is that constant. So look at that. We found the limit of the difference quotient from the right equals the limit of the difference quotient from the left. And so since those two limits are equal, I conclude, therefore, the limit as h approaches 0, period, of f of 0 plus h minus f of 0 all over h, in fact, equals negative 1. It exists and equals negative 1. And since the limit of the difference quotient exists, I can say, therefore, f is differentiable at x equals negative 1. And if we take a look at the graph of f of x, how cool is that? We have a line and a parabola that meet at the origin, and it is a smooth transition. How cool. The line slope smoothly transitions into the parabola, making this function differentiable at x equals 0. Let us now work on example number 6. F of x is another piecewise function. Part A is the same. Prove that f is or is not continuous at x equals negative 1. I think you should press pause, write out your work, and then I will highlight my work. Press pause now. And here is my work, and the final conclusion is that f is continuous at x equals negative 1. I think in example 5 I said at x equals a, but I probably should have said in example 5 at x equals 0. So I am making up for that here. F is continuous at x equals negative 1 is our conclusion at x equals negative 1. Now we're going to do part B. F is or is not differentiable at x equals negative 1. I'm going to go ahead and tell you to press pause again so that you can try to do this, and then we'll check our work together. Press pause now. Okay, let's go over this. I wrote the general statement. I'm inquiring whether or not that exists. I'm finding the derivative from the right, which is the limit of the difference quotient from the right. I have to plug negative 1 plus h into the right, so I have to plug it into 3 minus x, and that's where I get this bracket here. That's for this here. F of negative 1 is f of negative 1. Again, that doesn't change. That's determined by the equal statement. That's always going to equal 4 in this example. So I'm just going to go ahead and jump down here. That's why this is also equal to 4. Because if I plug in negative 1, I actually get 4. But you will see here on the bottom half here that I'm plugging negative 1 plus h into the bottom form. That's because we're finding the slope from the left. Delta x is approaching 0 from the left. And so that creates this portion here. And when I do the limit of the difference quotient from the right, I get 1. When I do the limit of the difference quotient from the left, I get negative 2. Those are different. Hence, the limit of the difference quotient does not exist, and therefore f is not differentiable at x equals negative 1. Now, in this graph of f of x, the parabola meets the line at a way that it is a sharp transition, because the slope coming in from this direction is a negative 2, but as we come in from this direction, it's a negative 1. Not differentiable at x equals negative 1. Let's treat this final example with some care. If you just look at the piecewise function, on the top we have 2x, and that's what happens to the right of positive 1, and we have 2x plus 3, that's what happens to the left of 1. at first glance, as we get comfortable with slope, you should be able to see what looks like the slope from the right is equal to 2, and then the slope from the left is equal to 2. So you might say by observation, since the slope from the right is 2 and the slope from the left is 2, then it must be smooth or differentiable because the slope equals slope. That observation is sound, except that mathematically they both won't work out to 2, and that's the point of this example. And here I wrote out the formal proof for why the function p is not even continuous at x equals 1. I don't think you need the formal proof to see that we have two parallel lines. One is higher than the other, so there's going to be a jump discontinuity. Now, a proof for why it's not differentiable is actually not even needed here. See, we talked about that theorem. Once we know that p is not continuous at x equals 1, then we automatically can jump to say that p is not differentiable. But what I'd want to investigate is, yes, I can tell that it's not going to be differentiable, but I'm still concerned that the slope is 2 and the slope is 2, and somehow if the slopes are the same, it's supposed to be differentiable. But I want to show why the math will work that out so that we're not actually getting the limit of the difference quotient to exist. Now, I know I'm speaking fast, but let's do the math portion for part B, and I think this will all come together. So here we go. Again, I just want to emphasize that I don't need to do this proof. I already know that it's not differentiable because it's not continuous. We're simply looking at how this manifests itself mathematically. So p prime of 1 from the right is the limit as h goes to 0 from the right, p of 1 plus h minus p of 1 all over h, which equals the limit as h goes to 0 from the right. 1 plus h has to be plugged into the top. 1 plus h minus. Now, this actually becomes an important part of this. P of 1, which I left up here, is 2. That will not change and actually ends up being the reason why the math does not work out. Appropriately does not work out. Okay, so if I do this, I get 2 plus 2h. The 2's cancel, and I'll have 2h over h after the limit. As h approaches 0 from the right, I'll get 2h over h. This simplifies before I plug in, so I'm going to keep the limit statement going. 2, and so that equals 2. Well, that makes sense. We could observe from the beginning that the slope is approaching 2. Here's where it all comes together now. I'm going to find p prime from the left of 1, which is the limit as h approaches 0 from the left. P of 1 plus h minus p of 1 all over h, which equals the limit as h goes to 0 from the left. We're going to plug 1 plus h into the bottom. So that's going to be 2, 1 plus h plus 3. I'll put a bracket around this to correspond with a bracket around this. And then this second part, p of 1, does not plug into the bottom, because when we have equals, it always plugs into the top. So that's why this stays 2. And that's why when plugging in 2, it's sort of displacing it away from the 2x plus 3 line, which is going to make something go haywire here. Let's see what I mean by that. So as h approaches 0 from the left, distribute 2 and 2h and 3. So that's going to be 5 plus 2h minus 2 over h, which is then the limit as h goes to 0 from the left of 3 plus 2h over h. Now I'm just going to break this into two different limits. Limit as h goes to 0 from the left of 3 over h plus the limit as h goes to 0 from the left of 2h over h, which is 2. See, this one here does not exist. Specifically, it's negative infinity, but it doesn't matter. It doesn't exist. And since it doesn't exist, it's impossible for this to equal this. So it's not necessarily slope approaching. We actually get down to the raw definition of what a derivative is, and we find that the right-sided derivative doesn't equal left-sided derivative. Hence, the limit as h approaches 0, period, of p of 1 plus h minus p of 1 all over h does not exist. Here's a picture of the function p. P at 1 was 2, so that's this. When we did the limit of the difference quotient, we essentially are taking points, getting closer and closer and closer and closer to the blue point, and that's why that slope is approaching 2, a slope of 2. But when we did the other line, we're picking points here, 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 but then we're comparing it to this point here, and it's creating chaos, and then mathematically it proves that it is not differentiable. In conclusion, number 6, we found that the derivative from the right was -1, and the derivative from the left was -2. Since those are both real numbers but different, we classify that as a corner. Specifically, a corner at x equals -1. It was not a smooth transition. It was not differentiable. But in number 7, the derivative from the right of 1 was equal to 2. But the derivative from the left does not exist. In the event that one of them is a real number and the other does not exist, that's when we know we have a discontinuity. In this case, specifically, at x equals 1.